So with this additional tool, what sort of structure do we see in the hidden representations at different points in training? Well, it's really quite remarkable. When we start off, of course, we've initialized this network with small weights. It basically is just always outputting 0 in the hidden activity patterns, and so we just have sort of a blank canvas. Initially, all of the items are not similar, or sort of equally similar, they're just all 0. And then after this first transition, we can see that all of the items have become similar to each other. So we just get a block of similarity structure. This corresponds to learning what they all have in common. So features that are held by all living things. Then after the next transition point, you'll see that we now have these big block structure. So this is separated off, for instance, the animals from the plants, where now all of the animals are more similar to each other and all of the plants are more similar to each other, but we know that the animals and plants are somewhat different. And then after the next transition, you see that we've elaborated each of those blocks further with a finer scale distinction. This might be fish versus bird or tree versus flower. And then again, we get down to the leaf nodes, and you have this characteristic structure of blocks within blocks, which indicates that the similarity structure reflects the hierarchy that's there in this particular example. So this phenomenon is called progressive differentiation. It's a feature that's been argued to hold for human semantic development, where children show similar progressions, where they start with broad categories before successively refining to these smaller categories. And we can see that indeed each one of these narrow deep linear network driven transitions is corresponding to an elaboration of one level of the tree. Now, that's all quite interesting, but you might have a little worry in the back of your mind, which is we're training a deep linear network. So aren't we just doing linear regression? After all, the input-output map that we're learning is always linear, right? So if we're looking at what this deep linear network is computing, it's just computing the product of all of its weight matrices times the input. But linear compositions of linear functions is still a linear function, and so we could always rewrite this product of weight matrices as just one single weight matrix. So it's not clear that depth is really doing anything for us. And you may be wondering why we're seeing this behavior, given that linear regression might seem like it wouldn't do very much here. Well, let's compare them and try to understand this a bit better. So for linear regression, rather than running gradient descent, we actually know what the optimal weights are. We can solve that problem directly. And so now your task is to see whether at convergence, the total weights from the deep linear network end up matching those that you get from this formula for linear regression.